Hello to everyone. So, you obviously see something strange here. This is the longest day. It's like 7 talks, so we decided to kind of spice it up a bit to wake everyone up. No, that's not true. The truth is, I have to share you this wisdom. This wisdom is, and you better remember it, is like, don't go and drink with Kate and Robin. That's the first axiom. If you go, don't drink too much. If you do drink too much, don't make stupid promises. But if you make stupid promises, then make them drink as much as they won't remember the next day. And unfortunately, I failed, at all the points. This is the proof. So. And I'm not telling you what Robin has to do now. So, okay. So, all right. So everyone, until I erase it, you're supposed to stare at it every once in a while. Some kind of announcement. Okay. So what I will talk about is it's what's in the title. As usually, if I go too fast or I go too slow or whatever, you have a question about the talk, just shout it in. Don't wait. I like when you're shouting questions, and I like when the talk is alive. Okay, so what we do here, the basic question we want to understand is the following. I start with a finite complex. Okay, I take its fundamental group. I call it gamma. Okay, so here's my finite complex. It's not very complex, but it will do. And the deal is that, the next thing you do when you want to understand that this complex has a certain, this complex can come from a Riemannian manifold, your favorite finite volume Riemannian manifold, or it could be, it doesn't have to be a complex, it can be just a finite volume space. That's fine. Anyways, you have nice invariants, and you want to understand those invariants. Okay, and that covers a lot of the modern mathematics. So one thing that people do a lot of the time is that they pass to the universal cover. So they take the universal cover, W tilde, which is, in the interesting cases, gamma is infinite. So that's an infinite complex. It's an infinite complex, but it admits an action. Gamma acts on the universal cover compactly. And if you take the quotient of that action, you get back the original complex. Okay, and somehow the deal is that there is this finite word, there is this infinite word, and then there are finite invariants, and there are natural analytic infinite invariants. And so you sort of want to connect them. Okay? So a typical example that we will discuss here is that you can take Betti numbers, so-called Betti numbers of the finite complex, and you can take L2 Betti numbers of the infinite complex, and then you want to relate them. So, or in general, you just want to relate structurally. You want to relate the complex to its universal cover. Okay. So if so the abstract question is what is the thing that connects finite to infinite? And we are mathematicians, but if we would be ancient Greeks, then the answer would be immediate. It is eros. Eros is that connects finite and infinite. And eros means both love and desire. And this talk will concentrate on desire, because it will be a lot of conjectures, but not a lot of theorems. So the deal is basically that you take a finite index subgroup, gamma n of gamma, that is a good subgroup in some sense, and we will discuss what good subgroup means. And then you take the covering, it's a finite index subgroup. Well, it's actually a sequence of finite index subgroups. And then you lift W with respect to that finite index subgroup, which just means that you consider Wn, which is the universal cover, modded out by just the gamma n action. So instead of the gamma action, which is a co-compact action, you look at just the action of that finite index subgroup, you mod out by that, and you still get a finite space That's your Wn. It's bigger than this space, and there is a covering map there. So instead of opening up your complex to infinity to have trivial pi 1, you just start to open it up and you stop at a finite level. Okay? And then this is kind of the eros. This is the object that will connect the finite and the infinite world. Well, at least in a lot of the cases it will be. It will, and conjecturally this is a general picture for many interesting invariants. So let me tell you examples where we know that there is a connection, and this is somehow the main topic of this talk. So probably the nicest example here. I mean, there is a covering here, and then there is a covering here, and well, there are two things that I have to say now. The first thing is, what does it mean that when is it a good cover? When do we say that it's a good cover? I tell you an example when we don't say that it's a good cover. You have say you have a complicated free manifold, okay, that fibers over the circle, so pi 1 surjects on Z, and you just take deeper and deeper cyclic covers. I mean, you just gamma n is walking down on that Z part and never sees the normal subgroup below. Then this Wm will look like bigger and bigger donuts. It will not look like the universal covering space. It's a very distorted image of the universal covering space. So that's something we don't like. If you take and then the standard way to do this, and I write it here, is to build a ladder or a chain. So one standard way to do this is to build a chain of subgroups where the subgroups are normal, gamma I are normal in gamma, and the intersection of gamma I is 1. Okay? So that's usually the nicest solution because these covering spaces are very homogeneous themselves when it's a normal subgroup, and you can use that to prove things. However, we could be happy with that, but usually we aren't entirely happy with just taking normal subgroups with zero intersection, and I go into it via little examples. So anyways, the general notion that we want to see here is that this guy, this intermediate thing, this very large object, it should look more and more like the universal cover. Okay? And the right language for that is Benjamini-Schramm convergence, the so-called Benjamini-Schramm convergence, which is a very simple thing. You just want the following to hold. So I call it the star property or approximation property. So you want that for every radius bigger than 0, you pick a random point, you pick a uniform random point in that complex, you look at the R neighborhood, you look at the R ball around that point, and you see what you see. And what you see is, with very high probability, with probability tending to 1, is the same as what you see when you take an R ball here in the universal cover. Does this make sense? So that's when we say that it's a good approximation everywhere with probability tending to 1, the sampling, random sampling, oh, I hate that phenomenon. Can you stop this from happening? No, you can.
Yes. You can turn the screw.
What? Oh, cool. Great. Better. Okay. So the random sampling at radius R converges to the random sampling of the universal cover. Okay? So if you have, that's one of these notions. If you have seen this, then of course you understand. If you have never seen this, then maybe this is you. So let's have an example. So my initial graph is just some free regular finite graph. Okay? Some finite graph where every degree is free. Okay, what is the universal cover? Hello, I'm talking at you guys. What? Free. It's the free regular tree, right? So what is a good intermediate object? It's a free regular graph. It's a free regular big, huge finite graph which has large so-called, from most points, the injectivity radius is large, the girth is large. So from most points, it looks like the tree in a big neighborhood. Okay, that's a good approximation. So that's the notion we are looking at. Okay, so, and the general theme is, and that's the general picture is that you take your favorite invariant. So this is kind of the machine. Take your favorite finite invariant, look at a sequence of covers that converges to the universal cover, and decide whether those invariants converge. Normalize the right way; they will converge, and then decide what it converges to. So name the infinite object, then do analysis, build an analytic theory of the infinite object, and then then be happy. Usually, then you can use the infinite analytic theory to get back new results on the asymptotic behavior of the finite objects. Okay, so the machinery is take your invariant, finite invariant, f, okay, look at f of Wn normalized somehow, and take the limit. Is there a limit? If yes, what is it? Meaning, what is it? Meaning, describe it, if you can, describe it straight from the limiting object. So find a definition that does not use these approximations, just uses the infinite object immediately. Okay?
Could you read the first point once more?
Which one?
The first.
Take your favorite invariant, f. Yeah. Phew, you can't read my writing. Okay. Look at how it behaves, how the invariant behaves on this sequence of coverings. Okay? And then question, is there always a limit? There are different answers to that question. And try to understand the limit at infinity without using the finite approximations, and then use the developing theory. So let me tell you a very nice, pregnant example that this has happened. It wasn't done by me. Yes?
It's a picture of everything has a base point.
Well, if you want, yeah.
I guess you have to for this notion of convergence.
No, because I was rather vague here. And you don't have to. But you don't have to because, when you sample this already when you sample this finite object, you get a random rooted object, not one thing. And also here you get a random rooted object for the universal cover, so that's not a problem. It's okay. But yes, if you want, just imagine that this is a rooted object and this is a rooted object as well. But then this will be more painful if you really want to build a theory. So, okay. So what I really mean is that if you take this finite model and this infinite model and sample it at random points, then you cannot really make a difference probabilistically. You see the same thing with some small error. Yes? Okay. So. Okay, let's describe this theory. It was definitely not, I have nothing to do with it. This has happened before I was kind of reborn as a reborn mathematician or something. So, and this is the L2 Betty number business. So when f is the kth Betty number, Bk, which is just the dimension of the kth Q homology, okay? The kth homology over the rationals, okay? Then the right normalization is to look at f of Wn, look at the nth cover, and divide it by gamma index gamma n. So we want to look at the growth against the index of the cover, okay? And indeed, there is a limit, and it will converge to the kth L2 Betty number of the original complex, which in nice cases agrees with the kth L2 Betty number of the group. Okay, so that's the story, and this has been done by, basically it has been done by Luc, the convergence theorem, although that was not exactly the language he used, and it wasn't such a general result, but mathematically it's his theorem, it's his result. So the proof is his proof. So So that's an example, and then you can have many questions. And for example, when this is a particularly nice case, it's it's when you're not like the Greeks, for the Greeks arrows could come basically from anywhere, and it was welcome. If you look at the more strict philosophical thinking, that when you look at the Kabbalah, for example, where there is this notion of a ladder that leads from earth to heaven. So probably this chain of subgroups that can be understood as a ladder. It's a sure thing, It's like each object is covered by the next object. It's a tower of coverings where you can just climb up. So and or not. But if the intersection is 1, then you can. And then this is in some cases this is a nicer object than just any sequence from anywhere, any wide sequence. For example, you can prove, if you look at the rank D of gamma n, the minimal number of generators, then you can prove that the normalized rank converges over chains. The rank normalized by the index converges over chains, and you can prove that the limit, you can identify the limit as the cost of the projective limit of the corresponding actions. This is a work of mine with Nick Nikolov. And so kind of there is a half-happy answer, at least for chains. There is a limit that you can identify the analytic invariant. It converges on chains to the cost minus 1 of the limit action. So that's fine. That's a happy answer. Cost, Damian already discussed cost, so I don't have to. However, there is still the question whether different ladders, if you have 2 different ladders leading to heaven and you climb up, whether you get to the same place, which is, of course, an important question for religious people. And the answer is that we don't know, which is probably an honest answer here. And we don't know. We believe that we do get to the same place. So we believe that if you take 2 normal chains with trivial intersection in a finitely generated group, then the growth of the rank will be the same. But we have no idea how to prove this, so this is out of reach. Of course, if you could prove the first phenomenon, that the limit exists for any sort of approximating sequence, that would give you an affirmative answer, because you can merge the 2 towers. You get 2 ladders where you hop from one ladder to the other, and that's how you get up. So, and it still converges. It must converge to the same number. So, but we have really.
Yeah. Is it true even for sequences of subgroups? Can you make such an argument if the limit always exists?
For chains of subgroups? Yes. They don't have to be normal. Is that what you're asking?
I mean, for normal chains, if you have 2 normal chains,
yes,
then the limit always exists. I mean, for any normal chain, can you also conclude that it's always the same limit?
No, the limit always exists for rank. For any chain, the limit exists. For any given chain, the limit exists. Yes, in that case. But I cannot make that statement, because that's something where we get stuck already at the rank. So this is pretty much not clear. And one of the reasons why it's not clear is that a covering tower is a particularly nice way of converging. So you can then there is a natural projective limit, and you can play with that very nicely. So it's not so clear what such a limit would be for just a sequence of actions. When you take such limits, usually it's an ultra limit or ultra limit. I never knew how to pronounce that, ultra limit or ultra limit type of thing. But that's much less amenable to doing math than just a covering tower. So, okay, so that's the deal. So, and the stuff I want to discuss today is just a modification of this. Is when you don't look at rational homology, but you look at homology over a finite field, Betti numbers over a finite field. So open is that f is the bk over fp. So p is a fixed prime, say prime 2 is already probably the hardest case, if that makes any sense, of W. So it's the K-Betty number, but over a finite field. Okay? So there we simply don't know anything. We not even we don't know that it must converge. We also don't know that it converges on chains. Even that is out of reach at that point. Nice normal chains with trivial intersection. It's still not clear that the normalized Betty numbers, that you do the same kind of normalization. So you look at BK, FP, WN divided by the index of the cover. Okay? And I put a lot of question marks here because that means that we have no idea what's going on. So we don't. So okay, let's summarize our ignorance. So we don't know that it converges. We don't know that it converges on chains. We have. No one has a well-built idea of what the limit should be, or how to define it at the limit. You know, at the universal cover. I forgot to tell you this L2 Betty number, which I'm not going to discuss. This can be defined straight, you know, without all that machinery. It can be defined on this space. So it's really an infinite analytic invariant. So this very sad moment came when I have to erase the announcement. So that doesn't make a big difference, but if you want, let's make a vote. You know, this is like a. How many people read this? Hands up if you read the announcement. Okay. I give you one more chance. Okay. So I'm impressed. So that means that you were reading that and not what I wrote to the board.
It was much more legible.
Yes, but I'm wearing a tie. You know, that should help. So, okay, I'll try to write with bigger letters. Okay, any questions so far? So that's the basic question. Basic question we want to understand. You take a finite complex, you fix a prime, you take some approximating sequence of covers that approximates the universal cover, and you look at the asymptotic growth, the growth of the mod P Betty numbers. Okay, does it converge? So there is a machinery with which you can translate this to the following setup. And, you know, somehow the idea behind this, am I done with this? Yes. So our best shot at this is that the notion behind it is sofic entropy. Okay, so that's the next deal. That's the limiting invariant. The limiting invariant will be a sofic entropy type invariant. And the other bet that we want to make is that you have to forget about linear algebra. It's not about, you know, well, the Betty numbers are just, you know, sizes of, dimensions of kernels of nice linear maps, right? I mean, the Laplacians. And our bet is that you don't care so much about that it's a linear map. You just want to use the fact that it's a locally defined map. And I will tell you what I mean by that. So, which kind of kicks out homology from this picture and brings in statistical physics. And you both decide for yourself whether that's a lucky change or not. But okay, so here is the deal. I just write up this conjecture that I have with Balazs Szegedy, and then we will connect the dots. The first thing that I have to tell you is what entropy is. So K is a finite distribution. Meaning just a distribution on a finite set, a measure on a finite set of points. So it looks like, you know, K1, K2, Kn. And I just, you know, ruthlessly and dictator-like define the entropy, H of K. This is the Shannon entropy as the, you know, the sum minus the sum of Ki times log Ki. And I'm not just, if you've never seen this, this is the Shannon entropy. If you're not familiar with this notion, I don't want to convince you that it is the right thing to look at. just believe that what it encodes, what this number encodes, is the amount of information, the amount of randomness in this finite probability space. So the stuff that you want to remember is the amount of the amount of random bits you have to toss to generate this this distribution, to be able to generate this distribution. Does this make sense? Okay. So if you believe that, then you also believe, at least, or you can actually also prove it, that if you take independent random variables with distribution k, so you take k to the x. By k to the x, I just mean that you take a finite set x, and you independently color each of the points of x with the distribution k, then the Shannon entropy just adds up. X times h of k. That's something we will use, so that's why I write it. But so when you take independent copies, then the amount of randomness you need to generate the distribution adds up. Okay, and also another thing is that if you have two finite distribution, two random objects, and one is a deterministic image of the other, a deterministic function of the other, then this decreases the entropy. Okay. This is very clear because one way to generate the second thing is to generate the first and then apply the deterministic map, and there you go. You got the second object for at most that amount of randomness. Okay. So I think that's all. I mean that's what we will use about this, and that's a notion that has of course an infinite literature. This amount of randomness. So the basic question that people ask is, and which is not very well understood still, and if you have a group, I just write it here because that's not the way we will go, but it's a big open question. Open question. So gamma is a countable group. C is an invariant random coloring. Of gamma. Okay, what is entropy per site? What is a meaningful notion of entropy per site? Okay, let me define what I mean by that. So you have your infinite group, okay, and you take a random coloring of your group where the randomness is invariant under the group action. This means that when you pick a random element according to your randomness and translate it with some fixed element of the group, that's another random coloring of the group, but it's the same. It has the same load, the same distribution as the original one. So the individual colorings are not invariant. The distribution of the colorings is invariant. Okay. So there are a lot of the interesting combinatorial questions, like Szegedy theorem, can be encoded into questions about invariant random colorings of Z, for example. This is Furstenberg's breakthrough proof for Szegedy theorem. That was the base of it. So we really want to understand these things, and one of the natural questions you can ask is whether there is a meaningful, for infinite groups, whether there is a meaningful notion of how much randomness is in such a system. Now, of course, the amount of randomness in the whole system is infinite, unless it's a really stupid random coloring. So you want to average. You want to know how many falls on a given vertex, how many randomness falls on a given vertex. The answer is that we have a very beautiful, well-built, solid theory for amenable groups, where basically any notion you could, if you've never heard this notion, and I pressured you to come up with definitions for entropy per site, you would come up with 4 or 5 definitions, and all of them would work, and all of them would be equivalent, and and people prove that it's all the same for amenable groups. Okay, and that's a beautiful deep theory. However, for non-amenable groups, as Damian pointed out, this axiom that I never wrote simply fails because the 2 shift, when you independently color the free group, you take the free group on 2 generators, you independently toss a coin on each site, And then there is a deterministic function, a factor map, which will be the full 4 shift. It will be independent 4 colorings. And up to any human beings, that should have more randomness per site than the original one, and it does. So a deterministic map can actually increase the entropy per site if you have any meaningful entropy notion. So that's behind that whole thing, and this got the whole theory, entropy theory, stuck for 20x years, where x is a number, until Louis Bowen came and proved that, yes, that's true, factor processes are not so cool, but for sofic groups, you can build a meaningful entropy per site theory. So that's somehow the story behind, and we will discuss this, but let's go back to this original notion. Okay. Let me just take the simplest version of the conjecture, because I don't want to go into define Benjamini-Schramm convergence in its full generality. So you can do the following thing. Okay. So let Gn be a sequence of finite graphs which converges to some infinite graph G. Okay, what does it mean that it converges? So G is vertex transitive, first of all, and this axiom holds. This axiom holds. If you take your finite graph, then for any fixed radius of sight, if you sample Gn at a random place, you see the same as what you see from G. And here even the objection that Laura made, which was a right objection, it doesn't play because the vertex sensitive graph looks the same from every point. Okay? And star holds. This is what Benjamini-Schramm convergence is. Okay, does it make sense? This is crucial to understand. Okay, so we have a sequence of finite graphs, and it looks more, probabilistically, it looks more and more like one infinite beautiful model. Okay? And the next thing, let kappa be a finite probability space, finite distribution. Okay? And also take a finite cellular automata. So so let A be a cellular automaton. Okay. So, well, these are the players of the conjecture. And basically, the players are the following. I tell you the players, and then you can figure out the play, which is usually not good news for real-life plays. So the players are the cellular. There is a fixed cellular automaton. There is this sequence of finite graphs that converges to some infinite object. And then there is this fixed finite distribution. And then there is the notion of entropy. Okay?
And what kind of cellular automaton?
Any, your favorite one. Finite. Oh, yes. No,
over
G. Over G. So by finite, I tell you what this is. Okay, thank you for the question. So finite all over G, over the limit, over the vertex sensitive graph. This means the following: a finite cellular automata is not something difficult. It's a recoloring machine. So here is your G. Just imagine that it's the free regular tree, because that's a complicated enough object. That's your G, okay? And the finite automaton is something that looks at the two ball around for every point. First of all, you colored your tree somehow with a fixed number of colors, say 0, 1. Then the automaton looks at the two ball around a given vertex. Okay, he sees some finite information there, right? And based on that finite information, the automaton makes a decision how to color this vertex. that's a deterministic decision. Okay? A very good example is that it counts how many zeros and ones are in the 2 neighborhood, and it chooses the majority. And if it's equal, then it colors it to 0. Does this make sense? That's a finite automaton.
Well, if G is vertex transitive but not simply transitive, then you have to really decide how you identify the neighborhood.
Yes, but it's annoying, but you deal with it.
So you ask the rule of the automaton to be invariant under all.
Yes. If you just look at the graph as a graph object, then automatically, otherwise it's not well defined. You want the rule to be invariant. If there is also some edge labeling, then you don't ask it. Then you ask the symmetry that you have to ask, so that it's meaningful. Okay, does this make sense? So this majority function, this looks like a trivial thing. There is non-trivial math behind. I mean, if you look at bigger and bigger balls, and look at the majority function and take a limit, then it's very, very fresh research to understand what's going on in the limit. Already for this, which is kind of a first non-trivial example to look at. So, anyways, the main point is that you do this simultaneously at every vertex. Okay, so I build you this finite automaton, which is really like a machine, and then I put the same machine on each vertex, and I push the button at the same time, and it simultaneously recolors the graph. Does this make sense? Okay. So this is what it means to apply a finite automaton on a coloring. Okay. Now, when I have a random coloring.
One more question.
Yes.
The finite distribution has the same set of states 1 to n as the automaton?
Not necessarily. You don't. Yeah, I shouldn't call it a cellular automaton. I should call it a cellular map, right? You don't care. You never apply it twice. So if you.
The states.
No, it could be different state space. The end result can be completely different from the beginning. It doesn't matter, not for the question that I'm asking. But okay, so that's the setup. And now, so if I have a random coloring, and I apply this fixed automaton on the random coloring, I get another random coloring. The funny thing is that even if you put IID on the vertices, independent random, so the kind of the most stupid randomness, the richest randomness you can, some fixed finite automaton can completely screw up the image. The image can be a very non-trivial random coloring with various properties and questions, and what can you get and what can't you get is an actively researched area in probability theory. So it's a very rich world. Okay, now we really defined all the players, and the conjecture that we are making is that then, if you take kappa to the gn, meaning you color the vertices of your graph independently with distribution kappa, and then you apply A on it, you apply your fixed finite automaton on it, you look at the resulting process, which is some crazy random coloring, and you look at its entropy, and you normalize it by the size of Gn. So you really look at entropy per site, which is meaningful for a finite object, because you just normalize by the number of vertices. Then this converges. Okay. So the meaning of that is that the amount of randomness that a fixed finite automata leaves in a system is continuous under this kind of convergence. That's the conjecture. Now, if you first hear that conjecture, even if you're in the field, like most probabilists, when I tell them this, they say, sure, that looks about right. One of the reasons why you would say that is that, if your automaton has radius 10, okay, and you choose 2 points that are farther than 20 away, then what you will see at the 2 roots are completely independent. They never disturb each other because I started with an IID. I started with an independent coloring process. And also, there is this correlation. You can see that the correlation decays very fast. I mean, you get very uncorrelated as the 2 points get very far from each other, and you can kind of believe that this is true. However, this is a risky conjecture. First of all, I would bet your house on it, but not my house. So that's one thing. The other is that even if it doesn't hold, that's also interesting. So I would love to see the counterexample, which is, if you're a psychologist or your parents were psychologists, then it means that I don't 100% believe in the conjecture. So, yes. Yes.
You color the edges of G or of
Yes.
G?
No. The vertices of G. Okay. Yeah, Gn. You never color G, actually. G is just the limiting object. That's the infinite vertex density graph. Okay. Let's cut off some parameters. G is the free regular tree. So you have a sequence of graphs where the graph tends to sequence of free regular graphs where the graph tends to infinity. Okay, that's what star means now. Curve tends to infinity, and you have a fixed automaton, and then you independently color your nth graph, your finite graph. You independently color with some fixed distribution. So that's like a mashed potato, right? And then you apply your fixed map on it, the automaton. That gets you a random coloring, and I cannot show you because that would take projector and fancy stuff, and I didn't do it. But this can get you very non-trivial random colorings. So, but and you take the image, you take that random coloring that you got, and you look at its normalized Shannon entropy, the amount of randomness that is left in the system by this automaton. Okay, and we conjecture that this is continuous in this convergence notion. So, meaning, if you don't like infinite words and convergence, meaning if you take two huge finite graphs that you cannot distinguish by sampling, then when you do this process, then the global entropy will be close to each other. The normalized Shannon entropy will be close to each other. Okay?
And you can do this with this one A defined on G because the graphs converge to G.
What?
The fact that you apply A on every Gn, the same automaton, and
yes.
defined on the limit.
Well, at some points it's not defined, but you don't care.
Yeah.
So at some points it's not defined, you just do whatever you want because that's what changed the entropy much. Good question. Yeah. Okay? It doesn't matter. At the bad points, it doesn't matter what you do. Okay? Yeah. Okay? For G amenable, we can prove this. When the limiting object is amenable, you can easily prove this. The usual quasi-tiling gives you that because by quasi-tiling you can break it apart. The breaking apart doesn't cost a lot, so it also doesn't cost a lot in terms of entropy, and then it's a simple counting argument. So for amenable objects, this is a fact. But that's a very, very we are very far from proving this conjecture. However, the good news is that this conjecture would prove everything here. If you settle this conjecture, then you get a big yes here. The big yes is that yes, the mod p Betti numbers will converge. The limiting object will be the so-called sofic entropy of the limit, and you get a very good understanding. You can calculate things and you can play around with it. So that's the deal. How much? When did I start it? I started it at. I have like 0 minutes. Okay. So yeah. So these are the things I would have talked about if I had more time. And I could explain how to connect the two things. That's one thing. What?
Is this known if the group acting on G is sofic?
No. Okay.
For G amenable?
No, just for amenable. It's already open for the free group. Okay? Oh, yes, that's what I will tell in the last 2 minutes. I just hand wave you what we do know. That's not a lot. Okay? So here is the thing. First of all, it would imply that if you take a convergent sequence of graphs, you take the adjacency matrix, and you fix a prime, then the mod p rank, the normalized mod p rank, converges. Because you can express it in these terms. So you fix a prime, you look at these matrices, and then it converges. The normalized mod p rank converges. We don't know how to prove that either. Okay? We don't even know how it in particular would imply that if you take a sequence of graphs converging to the free regular tree, meaning the graph tends to infinity, then the mod p rank converges to the full, to 1. The normalized mod p rank is almost full, which is, you know, if you're a graph theorist, that's a statement that feels like either trivial or probably not true. So that's why I call it a risky conjecture. Does this make sense, what I'm asking? Take a sequence of irregular graphs where the graph tends to infinity, look at the mod p rank of the adjacency matrix divided by the number of, prove that it must converge to 1. We already don't know how to prove that. Okay, what we can prove is that if you take random irregular graphs, then it holds. So if you take random irregular graphs, then the mod p rank is almost full. Actually, we have two different proofs now, which is a good news. One is Balazs' work with Agnes Backhaus using entropy theory. The other is more like representation theory. It's my proof. So you can prove it in various ways. For random irregular graphs, we hope that we can settle the general conjecture for finite automaton. This is in the works, and I'm kind of confident that it will happen. However, the overall picture is very much not clear. And the good news is, though, that if it's not true, I would love to see the counterexample, because if you forget everything about these L2 Betty numbers and so on, that graph theorists don't really care about so much, this is a meaningful question for graph theorists. If an automaton can distinguish two graph classes, that would be interesting for them. So if you can find me an automata and two classes of graphs that converge to the same object, for example, random irregular graphs and bipartite random irregular graphs, find an automata that fills them up. You know, the entropy fills which class it's sitting in. That maybe wasn't the right expression. You're from the UK, right? US. Oh, okay, fine. So I'm safe. So okay. So yes, if it can measure in which class it's sitting in, then that's a very interesting result for graph theorists. So don't stop yourself from thinking about it just because you want to be a nice guy and not screw our conjecture. Thank you. Also, Robin has a
question on automaton.
For the open question, do you know for a subscript of finite type?
No. I basically told you what we know. I mean, it works for hyperfinite sequences, so things which is the natural generalization for things converging to amenable, and that's kind of a few-line proof. And there is the random graph thing, and apart from that, we don't know anything tough.
And then you said that you knew it for like 3 regular, or you thought you did, that it converges. Is it like a nice function of the cellular automata?
No, wait, what? I didn't say that.
I thought you said it was in the works for 3 regular for the automata.
No, it's in the works, meaning that I'm hopeful there to finish it. No, we don't know yet. Yeah, there is nothing I can say there.
So you said you can prove it for the random irregular graph. Does this equal the F invariant of some action over?
That's a good question. We don't know. But the deal is that we're based on this thing, and that would have been the other thing that I wanted to tell you guys, but that would take 10 minutes, and I definitely don't want to torture people here, except Robin. Is based on this approach, we found a very simple one-page proof on Lewis-Bowen's theorem, the sofic entropy, Kolmogorov's theorem for sofic groups. So that does make a connection, and the proof is it's same theorem, but it's a much simpler proof. But we don't know. We define a certain invariant there, which we don't know whether it's the same as Lewis's invariant. This is not yet done. There is an inequality, but we don't know whether it's the same, and that leads to non-trivial statistical physics questions. So this is why I cannot answer your question anyways. I mean, until you identify it, it would be purely speculative to say anything about that. Yeah. Any more questions?
Yes, you said that you can say something for the majority automaton.
No. I said that already for the majority automaton there is deep research, ongoing research. Yes, ongoing research. There are nice results. Ask Balint about it. He knows a lot about it. Yeah. Okay, so, I want to give a present to the one who asked the most questions. So, Lauren, please. Thank you, guys.